here we go. We've got this to a nice boil. I don't know if you can see this in the camera. We got lots of bubbles and it's a nice creamy consistency with all that butter in here. And we're gonna stir it for 14 tablespoons, yeah. And we are gonna cook this for about 10 minutes.
For those of you who are wondering, that's 3.5 sticks of butter.
No. No, it's 8 tablespoons of stick.
8 tablespoons of stick. Oh, for those of you who are wondering, that's only 2 3/4 tablespoons of butter.
Yep, that's some math right there, Sarah. Good job.
Calculus.
Oh yeah, we definitely have our, elementary school math skills down, not even algebra.
Hey, that was like fractions, I think.
Okay.
That's like middle school, maybe 6th grade.
You did fractions in middle school? Oh, that's 3rd grade. I'm obviously in the accelerated program.
Clearly, considering you made it all the way to calculus before your junior year.
Yup. You know, calculus is really easy. This hard stuff is the adding and subtracting. I mean, I just can't do
multiplying
it.
large numbers.
I know, it's so hard though. I'm actually being serious. Like, the calculus is easy, and the algebra 2 is just ruining my life.
But that's what calculators are for.
Exactly. Who needs algebra?
I mean, they shouldn't have even taught us it. It was a waste of a year. We had calculators.
Yeah, all those teachers. Who needs Miss Armistead teaching us algebra 1? I don't need any of that. Mr. McGee teaching us geometry. My calculator can do all that. Okay, we're gonna go ahead and check the temperature of this now. We need to get this to
thermometer.
Oh yeah, it's very fancy. We need to get this up to about 300 degrees. And right now,
for those of you who can do math, that's 3 times 100.
Oh yeah. We are. Oh, it's still rising. We're getting pretty close, Sarah.
209.
212. Our candy is now at about 228 degrees. So you've got about, 30 to go? Who needs exact math? We're estimating here. Keep stirring. It's lots of fun. Smells pretty good. Lots of butter.
Oh, yeah.
So much butter. I like butter.
It smells like fat.
Yep. And we're not using lard, so we're going to keep it nice and vegetarian for people like me. I don't know, Sarah, do you want some bacon in yours?
Okay. No. Camera. Sarah, on camera shot.
Hey. Okay. Okay, Sarah, can you check the temperature, please?
All
Go ahead
right,
and grab that thermometer, we can swap places. Here we go. It's looking pretty good. Make sure it's not touching the bottom of the pan. We want to make sure we get the temperature of the solution, not of
the temperature of it surrounding.
Yeah. Why can you not do that right in the middle of our video? Or ask us, please? Sorry. Okay, Claire.
I was
Scooch. Go.
Shot my face.
Alright.
Sarah, let's hit the temperature again. Let's see where it's at right now.
We're at 254.
254. So we're getting closer. We're definitely getting closer. And our solution's getting a lot thicker. Look, it's nice and gloopy and gloppy, and it's very hot. Nice hot summer day, and it's making even more heat. No shortage of heat in the Wright household.
262.
Ooh, we're getting closer. Make sure I'm stirring all the way around.
That's right, Sarah. No, sir.
Okay, now I'm gonna take the spoon out. Oh, we're not looking for the soft crack stage. What are you doing, thermometer? Here, we're just gonna keep this in. That's alright that it's getting warmer than the soft crack stage, because we're not looking for the soft crack stage. We're looking for the hard crack stage.
This is gonna be some intense fudge.
Yeah, it's not fudge, Sarah. It's English toffee. What are you thinking about?
I don't know why.
And of course, the soft crack and hard crack stages are referred to the old-fashioned type of measuring the temperature of candy, where you get a glass of cold water and you put a little drop in, and it gets anything from a soft ball to a hard ball to a soft crack to a hard crack, and it describes the sugar's behavior in the water.
What an interesting fact, Sarah.
Yes, it is quite interesting, Sarah.
280 degrees, we're almost there.
Oh, but it's starting to get a little bit brown in here. Here we go. Well, now while this is finishing up, I'm going to go ahead and get our next stage ready. I'm going to get some parchment paper out so we can put our candy on. We're going to need a good long sheet of this because it's going to be a lot of candy spread out pretty thin.
After we make the coffee, what we're going to do is pour it out onto the wax paper and make it cool.
Wow. Okay, so there's our parchment. That should be enough for now. We can always get more.
296.
Oh, we're getting pretty close.
We're right there. 300.
300. Awesome. Okay, let me just anchor these corners. Now let's turn this heat off.
Quickly now.
And we are going to shake this up a little bit, make sure it's evenly mixed. Ooh, look at that nice brown color. Can you see that, camera? Smells yummy. Now we're gonna pour it, and we can pour it right onto the parchment on the tabletop because it's marble, so it won't hurt it. Yep. Can I see that spoon, please, Sarah? Make sure you get all of it out of the pot.
Oh, that is lovely.
Yes, it is gorgeous candy. Okay. Here we go. Now, Sarah, this has to cool a whole lot before we can do anything else to it. You know, I bet we could use Newton's law of cooling to figure out how long it would take, don't you?
I feel like that would be a wonderful idea.
Well, why don't we meet you guys back in the whiteboard and see if we can figure out how long it'll take for us to be able to eat this caramel. Of course, we have to add some chocolate first, so we'll need to look at that as well. Okay, today we are going to work on the Newton's law of cooling problem that we just discussed previously while we were in the kitchen. Now, Newton's law of cooling, written here above the board, shows that the time in which it takes for an item to cool is equal to the temperature of the environment plus the initial temperature of the item we're cooling minus the temperature of the environment, all just in parentheses, times e to the negative cooling constant times time. Now, the environment is 20 degrees Celsius, the candy is currently 100 degrees Celsius, and we need it to be about 25 degrees Celsius to eat it. So we're going to go ahead and plug these numbers into our equation. So we need the candy to be 25 degrees Celsius. The initial temperature or the environment is 20 degrees Celsius. And the candy is currently 100 degrees Celsius minus the environment temperature, which is, again, 20 degrees Celsius, times e to the negative kt. Now, the K, in this case, we're going to use the specific heat of sugar, which is negative 1.254, and that's going to be our K constant that we'll plug in right there. So I'll go ahead and write that now. Negative 1.254T. Oh, sorry. The negative is with the negative K is actually positive for the specific heat constant. That's always positive. So once we have all this together, we're going to simplify the problem down a little bit to where 5 is equal to 80e to the negative 1.254t, and 1 over 16, when you divide 80 off, is equal to e to the negative 1.254t. Now, to get rid of the e, we're going to use natural log, because the natural log of e cancel each other out, and we're just left with the exponent. So, the natural log of 1/16 is equal to negative 1.254t, and the natural log of 1/16 is negative 2.77, and that is going to be equal to negative 1.254t. We're going to divide both sides by 1.254, negative 1.254. And we are going to get a final answer of 2.21 is equal to t. So this candy, in an environment of 20 degrees Celsius, will cool from 100 degrees to 25 degrees in 2.21 hours. We can never forget our units with the word problem. Okay, back to the kitchen.